Okay, thank you very much. Okay, thank you for introducing me. Thank you, Nicole and Piotr, for inviting me to this wonderful place. And okay, so I'm from Nevada, and just to give you an idea what people do in Nevada these days, well, they do physics, but they also do this. I don't know if you've heard. This is called Burning Man, which is one of the biggest festivals in the United States, and we have people coming from all over the world. And this year, they got stuck in the desert because of the torrential rain. And you may have seen in the news, I had some friends who were kind of like really, really upset about this in the mud, pretty much. And cars wouldn't, of course, get them out of the desert because the climate is changing towards more kind of like mild in Nevada. So we're having these issues, hopefully. But also, I'd like to make a claim because the spin, I think, has it's actually a funny coincidence, but I don't think it's really a coincidence because Goodsmith was a professor at the University of Nevada towards the later, his later part of his career. He was at UNR and he taught. He liked Reno, but also this Burning Man take place in a place called Gerlach, which is where Burning Man happens. So I think it's really close. And this is a small town. There's like one gas station there, but we basically have two of the three. We don't have Uhlenbeck. That's the problem. But we have two of the three components of the spin inventors in Nevada. So that's for sure. Okay, so I have to do some sort of spin physics, right? Which is what I do. I do collisions and quantum dynamics, including spin degrees of freedom. But I want to talk before outlining my talk. I want to talk about this general concept of universality, which has been very successful in ultracold collisions, which is when you have people tend to think of ultracold collisions as dominated by long-range forces, but also short-range chemistry. And so these are two things that kind of drive ultracold chemistry. But and people have so far turned, they tend to ignore the short-range physics. They say, well, okay, there's a black hole here that just sucks all the waves and never lets anything out. But in principle, and of course, okay, this works very well, but this is very depressing. Because if you assume that there's a black hole, your reaction rate is determined by the mean scattering length, which is just the C6 coefficient and the reduced mass. And okay, there is some fundamental constants in there, but there is no sensitivity to the short range part of the interaction. So this is very depressing conclusion for chemistry, right? Because universal rate doesn't depend on the short range. So because of that, there is no information that you can glean from those experiments on fundamental properties of short-range collision complexes, which are so incredibly important. So universal experiments don't really cut it, so to speak. So we have to go beyond this and beyond the universality. What's there? There's a vast land of unexplored phenomena in ultracold molecular collisions, which basically one of the more well-understood phenomena is Feshbach resonance, which is when you have a degeneracy between entrance, open channel and closed channel. In the simplest case, the 2x2 problem. So then your amplitude of the wave function in short range is dramatically enhanced, and then you probe the details of short range potential, which is amazing. Which has been actually Feshbach resonances is what I'm going to talk about mostly today. So you see, this is an antithesis of universal. When you have a Feshbach resonance, you have not universal behavior, and then means this is super interesting and cannot be described by all this, very powerful but limited models based on, let's say, universal mono or multi-channel quantum defect theory with unit short-range parameters. So, but that's getting too close to too much into details. So Feshbach resonances are fascinating, right? So in atomic collisions, we know that they exist, and then in Rb and Rb collisions, there's a huge number of them in huge density. So also interesting for fundamental studies such as quantum chaos, quantum atomicity, and in atom-atom collisions, they seem to be well understood, more or less well understood. Although I wouldn't go as not completely, especially in the case of lanthanide atoms. There's still open questions in the field, but mostly. Now, in the case of molecules, very poorly understood. So what can Feshbach resonances give us when it comes to molecular collisions? And well, we can think about associating them into trimers and tetramers. And actually, the magnetic Feshbach resonance was first observed in atomic BEC condensate by Wolfgang Ketterle in 1998. And earlier this year, Ketterle's group also observed the magnetic Feshbach resonance in molecule collisions. And Alan is here, so all questions experimental question should be directed to you. but in many ways, these observations, in other modern collisions, we kind of understood what happened, but in molecule-molecule collisions, it's still an open question what exactly happens, because it turns out amazing thing is there's only one resonance over the huge interval of magnetic field between about 0 and 1,000 gauss, 1,200 gauss. And the big question is why there's only one, and what's going on? It's still a very interesting question, but molecule-molecule collisions are extremely complicated, especially those with alkali metal atoms. So I'm a theorist, so I'd like to understand things. And so I'm going to scale down a little bit for today's talk. And we're going to talk about Feshbach resonances in ultracold atom-molecule collision, which is also a wonderful field, which is opening up right now. So experiments coming, at amazing speed. So I try to be up to date here. I just last week, I think, a couple of weeks ago, there's this nice paper on VRX with Mikhail and Thijs and Ketter's group, Alan. So 3 of the authors of this paper are in the audience, at least. So I say no more about it, except that there is quite a substantial number of resonances, 17 resonances in one hyperfine state, and in one combination of hyperfine state, and also 8 resonances in some other combination of hyperfine state that was explored. So there's no shortage of amazing Feshbach resonances in atom-molecule collision. So there's that, and then there's also separate observation for potassium plus sodium potassium in Pan's group in China, also 11 resonances between 43 and 200 gauss. So what's going on? Like, what is the mechanism of Feshbach resonances in atom-molecule collisions? That's kind of the key topic of my talk. Although I'll talk about also this experiment in Kwen's group at Harvard, which we have been collaborating with, Rb plus Rb. It's another landmark experiment. It's extremely important for understanding the complex formation and deviations from statistical theories or arcane theories in ultracold molecular physics. So why ultracold atom-molecule collisions? Well, for theorists, we can do calculations, right? They're simpler. Because of that, there's fewer channels, and you can have there's a hope you can actually go and just do the full calculation without any approximations. This has been my dream, which I have been trying to make kind of, fulfill for many years, and we're coming closer to that, to the full realization, as I hope I'll convince you later. So in this talk, but there's other experiments. There is this rubidium calcium fluoride experiment, Michael Tarba's group here. Here in Europe, for me it's like very close geographically, but of course for you it's probably very far. But rubidium strontium fluoride is another experiment actually underway in David Mills' group at the University of Chicago, also important for sympathetic cooling for many other reasons. But these experiments I'll talk more about in the second part of my talk, which is again rubidium plus Rb experiment, where they observed a very, very long lived collision complex. For some reason, 5 orders of magnitude more that lived like forever, pretty much, compared to our KMS. Right? So no one knows what the hell is going on. Sorry, like in here. So I mean, we need to figure out if we are to have any hope of understanding this process. So this is really important. Okay, so theoretical challenges. I said it's easier than molecule-molecule collision, but it's by no means easy, especially for heavy systems such as sodium lithium, heavy, deeply anisotropic potentials. All the systems have. This is just a sample of, from this paper that we published a couple of years ago. Jacek Loss and Svetlana Kotachigova, they calculated the potential energy surfaces for sodium plus sodium lithium trimer. And you see there's a conical intersection. There is the potential is about 10,000 wave numbers deep. And the rotational constant of sodium lithium, just to give you an idea, is way smaller than 1 wave number. So you can fit in hundreds and hundreds of rotational states. And even on this relatively shallow potential, I think nice calculations is 300 that you can fit on this green potential. And you can imagine how many more you can live here, thousands, I would say. Yeah, thousands. So these computational techniques it's really basically challenging our abilities to do computations, but not completely, it's not out of reach completely. So it's a tantalizing possibility that we can actually analyze these resonances, using exact couple channel calculations. So all these challenges are there, but today I'm going to focus on 2 particular challenges that have remained unresolved up to now, which we have resolved, which is hyperfine structure. Hyperfine structure is the tiny splittings into nuclear spins, right? That actually important. They are larger than the collision energy, and therefore they need to be taken into account. But so far, no calculation has been able to do that. So that's because of enormous basis sets are required for convergence. So we need to use a more kind of clever approach to choosing our basis set, and so that we can actually solve the problem with the hyperfine interaction included. So there's also, of course, uncertainty. There's like a riddle with problems, pretty much. So, but we're trying to take them one step at a time and solve one problem at a time, and hopefully we'll get there. So this is just an illustration from this recent paper by Tice and Paul with Alan and Kepler's group. The depth of the potential of sodium sodium plus sodium lithium is like a few thousand wave numbers, and this just illustrates, this is the different basis sets that you use to run, to calculate the Feshbach resonances. And you see, depends on the basis set. The result you get depends on the basis. If you have 30 rotational states, you get this red line. If you get 10, or if you include 10 rotational states in the basis, you get this orange line. And these lines are essentially different. So the density of resonances increases as you increase the size of the basis set. And convergence is hard to achieve. And these calculations, as this calculation shows. So this is kind of like a summary of all calculations, which I think I've tried to be precise. And so I summarized all the calculations that have been done so far, or many calculations on strongly anisotropic ultracold alpha molecule collisions, the reactions that are driven by strong anisotropy. So that includes light systems that have been investigated earlier. So that excludes systems that do not pretty much contain alkyl metal atoms, which are very important as well, but it's just they wouldn't fit here. So anyway, so we have the pioneering studies were done by Jeremy Hudson's group, Jean-Pierre Launay and Bouin in like more than 10 years ago, where they showed that you can actually converge this lithium plus lithium to sodium plus sodium dimer and potassium plus potassium dimer calculations on the realistic potential. That was a big step forward, but those calculations didn't include nuclear spins, they did include external fields. So that was, and later on, Svetlana's group with Balo's group, Balkrishna's group at the University of Nevada, Las Vegas, James Croft and Brian Kendrick at Warsaw National Lab. That was K. They were able to do a converged calculation on K plus KRB. That was really an impressive feat that they achieved, because this required many thousand processors on these powerful computers at Warsaw National Lab to run. So that's by no means a calculation you can run on your laptop. So that's not that, just it's not going to happen. Okay, so this is an impressive calculation. Again, no external field, no hyperfine structure. So then we actually started in like about 10 years ago. We started including external fields in this kind of systems. They are slightly less anisotropic than the alkyl metals, but they do include laser cold molecules such as calcium hydride, strontium OH, and rubidium strontium fluoride. So in these calculations, we were able to include external fields using the total angular momentum representation we developed for that purpose when I was a postdoc with Alex Dolgarna at ITAM. But we still couldn't include nuclear spins. The calculations were too complicated. So there was this still sees there is this no colon. It means that nuclear spins have not been included in a way that is. I mean, people included them here and there, but not in a way that would be convincing as far as converged basis set. So on converged calculations use the nuclear spin basis sets, but no converged calculations have been reported as far as I know. So that's a qualifier to be put there, but there's a problem because nuclear spin hyperfine interactions are important, and also for collision complexes. There's been some indications that they affect the lifetime of collision complexes. So we better be able to include these interactions in coupled channel calculations, and this is what we did. So it's time to outline my talk, so I'll describe quickly a theoretical approach that we developed for this purpose, then present numerically exact calculations on rubidium strontium fluoride system in the rigid-rotor model. So and then I'll talk about this experimental Rb plus KRB at Harvard and what we learned from it. So very quickly, I'm a theorist, so I have to put up this slide. At the molecule trimer Hamiltonian, we already saw. So there's kinetic energy, the potential energy, intramolecular Hamiltonian. The intramolecular Hamiltonian, so the way we think of it, I recently started thinking about it as an open quantum system. So it's you may be familiar with the theory of open quantum systems. When there is a little system, there is a large bath, and there's a system bath interaction, right? So In this case, little system is just rotating molecule or rotating atom molecule, rotating trimer. There is spin bath, which is essentially this bath Hamiltonian, which includes all the nuclear spins operator couplings with with magnetic field, intra-spin couplings here. So you can think of it. Actually, we have a paper we're working on as a general. You can generally map out molecular Hamiltonian onto a central spin model, and you can use actually ultracold molecules as quantum simulators of open quantum systems, specifically the central spin model. So, this kind of issues aside, so I just want you to remember from this plot is there's this rotational part, which is a small compact system, and then there is a spin back. And there's this coupling. They're not uncoupled. There is coupling due to the fine structure, Hamiltonian, and an isotropic of tensor hyperfine. But these couplings are actually typically fairly weak. So this is an ideal situation for the system back kind of approach, right? Because you might be able to use perturbation theory, right, in this case, and you might be able to, solve. So this is a very physically appealing way of partitioning molecular Hamiltonian and thinking about the molecule in a different way, more like of a way of open quantum system. So we have done that. So we decided to use the product basis set. So we separate out rotation, in which we couple the molecular rotation with the orbital angular momentum of atom around the molecule, like this angular momentum, or the rotation of the molecule and orbital motion are coupled to form the total rotational angular momentum, J sub r. There are other notations. So Jeremy, sorry about that. So Jeremy used capital N to denote J sub r, but I use capital N for diatomic molecular rotation. It doesn't matter. So the point is that you separate out the spin. You tensor your basis states are tensored states with you only couple rotations within the system, and then spins are separate. So what that achieves for you is that it actually enables you to block diagonalize the Hamiltonian in such a way that all the important rotational interactions, including strongly anisotropic interactions, are block diagonalized, and the weak interactions are off diagonal. But who cares about the interactions, right? So basically, the hope is just to be able to take this little sub-block and do the calculation. And we have actually published, almost published, hopefully, in PRA, coming out. But it's on the arXiv with José Delpal from Vila. So I should also give credit to Jean-Michel Lemay and Andrea Simoni, who are the first to write down this basis, as far as I know. Maybe there are some other papers, but the credit belongs to them, but they never kind of explored it they never finished the calculation to show that this is actually a good basis set. We just used it. So, but nevertheless, we're not the first to look at this basis for sure. So, but just to give you an idea what we did, so we applied to rubidium strontium fluoride. We had excellent potential energy surfaces from Piotr's group and his graduate student, Maciej. Sorry, my Polish is not so good. So I also in this paper, you see the singlet and triplet potentials are very deep and very anisotropic. So this is very good case to apply to really test your basis set. If your basis set is any good, it should be able to solve this. If it's not so good, it will fail. So this is a challenging system because there's hundreds of rotational states that can fill up this well and this well as well. So this basis set, so we were able in 2018 to use total angular momentum. So we knew we could converge the results. So this is a convergence plot. Of course, section is a function of total number of rotational states in the basis set. So we knew that with 125 rotational states we could do it, but we didn't include the hyperfine structure. So that was an essential difference between that work that we published with Spectra, like before COVID, and then all the work that happened since. So this is a quick snapshot of results. So this is ultracold rubidium strontium fluoride. So this is a converged calculation of Feshbach resonances with 175 rotational states in the basis set. You see, this is just for comparison with zero number of rotational states. So you see that the number of rotational states matters quite a bit. So you cannot just approximate the results. So there's only two resonances in no potential with no anisotropy effectively. So anisotropy plays an important role in rotational states, and then we observe about up to 8 Feshbach resonances between 0 and 2000 Gauss. And this calculation includes the full hyperfine structure, and it has only one lowest total rotational angular momentum block in the calculation. So that's what enables these calculations, and we see that there's definitely potential for observation of Feshbach resonances in the systems. One limitation of this calculation, I don't want you to get me wrong, there is there's a rigid-rotor model that we use. So we didn't really include the vibrational mode of strontium fluoride, but we have reasons to believe that this vibrational mode in that particular system, strontium fluoride, doesn't have much of an effect because we have some previous test calculations of calcium hydride, which were included in all the 13 vibrational modes up to dissociation limit, and there wasn't much of an effect. If the molecule is softer, strontium fluoride is a little bit softer than calcium hydride, so there may be some effect, but again, that's what we can do, and these calculations kind of like open up the prospect. So we can actually add this one row to the table. Finally, we can say yes on 3 of them with hyperfine and converged rotational bases and external fields. Now, vibrations is the next frontier. So can we include vibration, right? Well, we think yes, because we definitely didn't fry our computers doing this calculation. So we have some room for more channels. We can include vibrational modes, but this is a separate project, and it remains to be seen whether we probably will wait for the experiment and see whether it confirms the density of resonances from the rigid-rotor model or it refutes the model. We'll see. So, but there's definitely a way forward for these calculations to go, and potentially. So this brings me to the next topic, which I have about 5 minutes. So rubidium plus Rb. So in another very challenging system, where this total rotational angular momentum basis was actually proven to be important and game-changing in this case. So recent experiment comes at Harvard. They observed transfer of hyperfine energy when rubidium atoms were prepared. So rubidium atoms were initially in the F equal to 2 state. They had quite a bit of internal energy, about 6 gigahertz, 6.8 gigahertz, and they collided these rubidium atoms with trapped Rb molecules in the ground rotational state. And what they observed is that rubidium atoms would fall into the ground state, but the Rb molecule would get rotationally excited, right? So this is very interesting. It means that there's some interaction that couples in essential ways, rotation with nuclear spin, right? So, and electron spin. In this system, there's an unpaired electron spin due to the rubidium atom. And so what's going on here, right? So before I go there, also Canquin's group asked me, well, I mean, they sent me this. So I'm a theorist, but I think it's also important to understand experimental details. So this is their previous PRX paper that reported anomalously long lifetime, which still remains a mystery as far as I know. So in that experiment, rubidium atoms were in the F equal to 1 ground state. So there was no possibility for inelastic scattering, right? So the rubidium was also Rb was also in the ground state. So the products, the Harvard group is of course unique in many ways, but one of the things that they know how to do is to detect the products. So they can actually detect the reaction products. So they can tell how many of rubidium atoms, for example, coming out in the ground hyperfine state, how many of the Rb molecules are coming out in rotationally excited states. So they can actually map out this, and they can actually, which is what they did. And so this is the important result they observed, that Rb was coming out mostly in n equal to 2, little n equal to 2. I apologize for different notation, but this is the rotational states of Rb. So they have n equal to 2 mostly populated, then n equal to 1 a little bit less, and then n equal to 0 with the smallest probability coming out. So how do we understand this intriguing result? So actually, most of the rubidium was observed in 1-1 state. So it never. So there may be some 2-2 remaining, but most of it in 1. So we actually set up this couple of channel calculations. So since this is what we do, right? And anyway, we have this Hamiltonian. It's very similar to the Hamiltonian that I described, like think of open quantum system, rotation, spin, and spin rotation interaction, right? So that's what a molecule is. Well, there are vibrations, of course, we ignore them for now. But the point is that the spin-dependent Hamiltonian for Rb is complicated, especially when it's interacting with potassium, with the rubidium atom, right? Also, there's no chemical reaction in the system, so there's only can be inelastic scattering. So we see the spin-dependent Hamiltonian has the hyperfine, atomic hyperfine, but the most important interactions actually is the Fermi contact hyperfine between the spin of the atom and the nuclear spins inside Rb molecules, right? So, okay, there's other terms, tensor and isotropic hyperfine, but and there's also spin rotation interaction, all kinds of terms. There's maybe like I stopped counting at some point, so there's many. So fortunately, Mikhail calculated many of these terms ab initio. So we actually he sent us his ab initio calculations for those isotropic constant hyperfine constants. We expanded them in geometric polynomials, fit the results, and here we go. We have the hyperfine interactions at least at our hands, and we have also potential energy surface, or a rudimentary version of the potential energy surface with just two lowest anisotropic terms. So, which we can use for scattering calculations. So this is what we did. So we employed the total rotational angular momentum basis. In this case, you have atoms also sticking here, or you have tensor product of atomic hyperfine states to take care of. And then the nice property is that the atom molecule interaction potential and the Fermi contact are diagonal in this J sub r, total rotational angular momentum. And because of that, you can solve as many rotational states as you want. So you can achieve converged results. And the other property is that the off-diagonal terms in J sub r are small. So all these tensor hyperfine interactions and they're weak. So what we have seen that we can actually converge the results using the assumption that the total rotational momentum is conserved. So this is a key point of debate that has been a while. People debated whether total rotational momentum is conserved in atom molecule collisions, and our calculations show, at least at the rigid-rotor level, that this assumption is very accurate to within 1%. So the total rotational angular momentum is indeed conserved. So that means that we can do, first of all, the good news that we can do with 600 channels, we can converge our couple channel results, right? And the second, it means that the observed product state distributions are probably non-statistical, because you can only get the statistical ratio 1 to 3 to 5 if you assume that the total rotational angular momentum is not conserved. So if you instead assume that it's conserved, you get 1 to 1 to 1, which is not what was observed. So it seems to suggest, although jury is still out, it's still somewhat unclear, but it seems that all data seem to suggest that it's not statistical that's coming out. So in order to explore this in a little bit more detail, we actually did a histogram plots. So this is like the result of average. And this is this rigid-rotor coupled channel calculations converged product state distributions. The histogram averaged over 40 different interaction potentials. So we basically took the potential, we scaled it a little bit, and then we just histogrammed the data. So we see that what these calculations predict is very different from what the experiment observes. So we say that most of the products are actually n equal to 0. This is what the calculations predict. So if we modify the potential energy surface a little bit further, we start seeing outliers in these histograms. It means that there are some weird potential shapes for which actually the products are coming out and they agree with the experiment in their distributions. But most of the time, the majority, 99.9% of the potentials do not match experiment. What does it mean? It's probably also kind of like a suggestion or suggestive indication that the dynamics is highly non-statistical in this case. So these are my conclusions. Open questions, we want to include vibrations and extend, maybe chemical reactions at short range. And here's some preliminary results. I just wanted to flash this slide from Conquen's knee group, and they observe Feshbach resonances in Rb plus Rb collisions. And they're there. We have no idea what's going on, what these Feshbach resonances are due to, but it's interesting. So there's a lot of potential in the system. I just want to thank Masato Morita, who was the driving force behind most of the calculations, who is coming here, as I understand, in Mikhail's group. And I'd like to thank Paul Bremer, the PI, Conquen's knee group, John Bone, of course, Abdullah. We have been having a wonderful collaboration, and I think Perter is becoming an experimentalist. So according to the picture that I found on Google Pictures. But okay, thank you very much for your attention.
Okay, thank you very much. Okay, we have a couple of minutes for some questions. Jeremy, I'll come to you first.
So I'm very interested in your rubidium plus strontium fluoride, because we've done some calculations in which we took a essentially totally different approach. You've taken the complete potential and hit it hard. What we did was to argue that the rotational excitation and all the short-range physics would really come through in terms of effective singlet and triplet scattering rates, and that apart from that, that kind of system was very much analogous to an alkali system, and rubidium fluoride, calcium fluoride or strontium fluoride was really quite, provided it was in rotational ground state, it was quite alkali metal.
Right.
And so we calculated resonances as a function of singlet and triplet scattering rates, and came up with fairly, and we then argued that there weren't going to be many resonances resonances due to the rotation of excited states
Mhm.
in the circuit. Robbie Bird's got a poster on this, but it would be really interesting, I think, to compare the full calculation with the kind of model that Robbie does. I mean,
Mhm.
clearly the masses are a bit different, potentials are a bit different.
Yeah.
It'd be interesting to see whether the general features of the resonance patterns you get
Yeah, so I would say
also
this
come
would,
out of a simple model.
yeah, this is what you would expect from a alkali metal-like calculation because there's no anisotropy in it. So in animal, it's a super simple calculation that's runs on a laptop, and you see that there are some differences. So you don't get the full density of resonances. You get a few resonances, you do, but rotational states, excited rotational states, seem to be important for this
So
calculation.
we certainly put a number on that and reckon that for a random potential there was something like a 19% chance that you would have
Right.
one or more resonances due to the rotation of excited states. So if clearly this is a specific potential rather than sampled overall.
For sure, yeah.
But there might be a difference there.
Yes, there is definitely. Yeah, this is why I'm showing this plot because I kind of anticipated this question. It's not entirely alkali-like. I'd like to be able to say, oh, it's just like alkali-alkali.
I
But
want
it's
to know how come, given the rotational constants, if this is a representative potential, how come that can be the case? Because we don't think that states can actually give resonances tuned by it.
right.
So
Well,
that we can look at it. I think it needs
yeah,
discussion.
definitely could be analyzed further. And I think we just got these results a few weeks ago. So definitely there's much to understand about these results.
I think we can probably squeeze one quick question in before we move over to the next speaker. No? Okay. I guess we can thank Timur again, and the next we can come and set up.